Hello, I'm Risto Miikkulainen, and I'm going to talk about how Cognizant's evolutionary AI can be applied to the problem of optimizing the non-pharmaceutical interventions in the COVID-19 pandemic. This is the big framework, the big picture here. How do we make good decisions in businesses, in organizations, in science, and generally in life? There are a couple of factors. We try to take past experience into account, do something that has worked in the past and might work again. But there's always an element also of trial and error. The situations are new and we have to try something, or maybe we want to try something that might work better than what we've done in the past. So this is what evolutionary AI tries to capture, and in particular, ESP, the evolutionary surrogate assisted prescription technology. So there are two components. The first one captures the experience part. That's the prediction part. That given a context where the actions are taken, we predict what the outcomes will be. And the second component captures the trial and error part, or the exploration part. Given a certain context, we'll explore what actions we should take. And each of these prescriptions are then evaluated against the predictor so that we can find out what explorations actually lead to good decisions. That's the general framework. So we've applied ESP to many decision-making domains and can it be applied to many more. For instance, optimizing designs of web pages so that users convert as often as possible. Optimizing recipes for agriculture, for vertical farming. Various behaviors for agents in games. And in business, in marketing, for instance, allocating dollars to different channels so that the sales and return on investment is maximized. So this is the general framework, and here we apply it to making good decisions about COVID-19. The idea is to optimize the non-pharmaceutical interventions using the same technology. And I have to emphasize that this is new. This is something that has not been done before. There are lots of models about COVID-19, and they are predictive models. They tell you what is likely to happen in the future, given some past history and decisions about the NPIs. And ESP brings a new element into this framework, and that is that it actually tells you what you should do, not just what will happen, but what we should do about it. So to build such a system, the first thing you have to do is to build the predictor. And here we take a little different approach than what's commonly done up to now. Most of the models, the predictive models, are epidemiological. They are based on simulation of differential equations. But here we are taking a machine learning approach, the data-driven approach that utilizes an existing data sets of cases and learns how to predict them in the future. We use a deep learning approach, LSTM network, and the Oxford data sets on cases and NPIs, the government response tracker. And on top of that, we add an uncertainty model that estimates how reliable our predictions are. So this network gets the case history and also the enacted NPIs, and predicts in the end how the cases will develop in the future. And once we've done that, we can evolve a prescriptor. And note that this has to be done differently because there are no gradients. We don't know what the optimal interventions might be. So there are no targets. Instead, we have to evolve these neural networks to make suggestions. And evolution means that we're using crossover and mutation to change the parameters, the weights on the network, and then evaluate a population of network based on how well they work. It's a population-based search approach. Then this is also multi-objective. So each individual in the population is evaluated based on how expensive the NPIs are that it suggests, and also how many cases there will be in the future. And as a result, we get a Pareto front. This is the population over evolution time. And we see here the number of cases and the cost or the stringency of the NPIs that the prescriptors suggest. And we see that we started with a pretty broad combinations of those values for the candidates. And towards the end of the simulation, most of the candidates are in this curve here. That's the Pareto front. Those are the optimal trade-offs between the two objectives. Low here in the figure, we have the least costly, least stringent NPIs. And on the left, we have the smallest number of cases. So each one of those is a trade-off, a different trade-off between the two objectives. And that's what is the result of evolution. We are giving a set of possible prescriptors from which a human decision maker can select the one that matches the desirable balance. So to make these ideas more concrete, we've developed an interactive demo that allows you to explore the prescriptions and predictions and outcomes. So here you go and pick a country from the map, like Italy here. And then you can pick a prescriptor from the predictor front. There's 20 different solutions that we've saved. This prescriptor is particularly stringent. It wants to make the cases go down as quickly as possible, and therefore it recommends all of these NPIs, from international travel to public transport to public events to workplace and school closings. All of those are active, and the cases indeed go down very quickly. So here in the prediction plot, we have the data, the actual data to the left, and then we have the forecast boundary, and then everything to the right is forecast based on these NPIs. Then you can go and select something else from the predictor front. So for instance, here we can go all the way to the right, and this is the most permissive prescriptor, and it wants to open up the economy completely, no restrictions whatsoever. And as you can see, that may not be a good idea. The cases start going up, and by October, they are actually peaking with a much higher level than ever before. So the interesting cases are here, somewhere in the middle, where there are trade-offs. So if we pick something in the mid-range, we see that some of the restrictions are still active: schools, workplace, public events to a lesser extent, and that still keeps the number of cases decreasing. But if you go just a little bit to the right, we, for instance, allow workplaces to open mostly, then the cases start going up. So these are the explorations that need to be done. You come with your ideas of how permissive or how open you might want to be, and then find where the boundary is, where you want to, how much you can tolerate the cases going up. So also, it's interesting that this can be applied to different countries at different stages of the pandemic. For instance, if we go to Brazil, it is in a different stage. The cases are still going up when we start making forecasts. So something here like maybe this prescriptor, which is relatively stringent, might work for Brazil. Some of these restrictions are already relaxed, international travel and stay-at-home requirements, for instance, but it's still enough to have workplace, schools, and public events closed so that the cases start going down. And again, if you move to the right, that will gradually open up more of these NPIs, and we'll get then eventually cases start going up. An interesting case is also Iran, because it seems to be at a start of a second wave. Here's the data, it seems to be rising again, and therefore something a little bit more stringent is required, maybe something like prescriptor 6 to keep the rise in check. Again, if you go to the right, we'll get into trouble. And US and UK have a relatively flat situation. So there, the cases are going down, but very so slightly. So it's pretty much flat and has been for a while. And there's an interesting prescription that comes up right here. The workplace are alternating between openings and closures. And this is an interesting result because it suggests how evolution can be creative. It does not have a whole lot of choice in the output, but it can open and close these various dimensions. And here it discovered that this kind of a soft opening is a good idea. If we open it completely, then we go too far. Perhaps we'll get that the cases start going up. But this kind of alternation is a creative solution. Maybe there are other ways of doing this. We could have workplaces open on alternate days, have some of the work move outside, improve ventilation. Those are the kinds of things that the prescriptors don't have access to. But this is the best it can do given the tools at its disposal. All right, so the conclusion here is that even with little data that we have today, we can already get some general conclusions from it. And one of them is that indeed, the schools and workplaces are the most important. We have to be careful in what we do in those dimensions, because it really has a large impact. And also that creative solutions are possible. And indeed, work and school is probably not going to be the same as it has been until now. We have to be creative about how we open them in order to deal with the pandemic. And this demo will soon be expanded. We'll include more countries beyond the 20 that currently are there. And we might create a scratch pad here where we can manually change some of those prescriptions and convince ourselves that these indeed are good. And also, we should allow counterfactuals. We should be able to go back in time and see, for instance, in the US, how we could have dealt with the pandemic if we had been more proactive and enacted something earlier on. Maybe a full lockdown might not have been necessary. So things like that are maybe too late for now, but it might still be time for say, Africa and other places, and also for any future pandemic to learn these lessons and apply them. So to conclude, what you've seen is a demonstration of a new approach to understanding pandemics. It's based on data and machine learning. We use a data-driven approach to build a predictor to forecast the outcomes, and we use evolutionary AI to build prescriptors, those neural networks that recommend different interventions. And as the data becomes more plentiful and better quality, we may eventually be able to build an actual system that supports human decision-making regarding COVID-19 and future pandemics. And the bigger picture is that the same approach can be used in other opportunities in healthcare, business, education, and society to help humans come up with better strategies for decision-making, reducing cost and improving lives. So if you are interested, this demo is available on the web on the URL below, and there's also a detailed paper that describes all the technology behind it. Thank you for listening.